Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to the next session on the subject of system programming with Linux. Today's session is a continuation of the previous session in which uh, we saw the overview of processes in the Unix-based systems. We talked how we can create processes using the fork system call. We talked about the importance of different IDs like the real, effective and saved UIDs of a process. And we also see how we can change them within a C program. And we also finally discussed the concept of process trees, chains, and fans. Dear students, if you have not seen the part 1 of process management, I strongly recommend that you should first see that and then fall back to this. Well, the agenda of today's session is, first of all, we are going to talk about the vfork system call. We're going to talk about the copy on write semantics that is used these days in the fork system call. We'll talk about the orphan and zombie processes, and we'll see how the parent process can monitor the child processes using the wait system call. We will dig out details and we will decipher the status argument of wait using the bitwise as well as the macros. Finally, we will talk about the limitations of wait system call, and we will discuss the other family of wait calls like waitpid, wait3 and wait4. So let's start playing. Well, dear students, the fork system call appeared in the very early versions of the Unix kernel. Consider a shell program. Every time a user executes an external command, the shell do a fork to copy its entire address space in the child process, and immediately after that do an exec system call to override the child process address space with the code of the external command to be executed. So it appears that vfork call is more efficient because it do not duplicate the virtual memory pages as the fork calls do. And moreover, the parent and the child both execute in the same address space. The second important point to keep in mind is that the execution of parent process is suspended until the child has performed an exec or an exit system call. Let me move on to the terminal and show you the proof of these concepts. And let me get vfork.c. It is not here. Let me move on to spvl and probably in 18. Let me get vfork1.c. Okay. This program proves that after a vfork, the execution of parent is suspended till the child process terminates. So the parent calls a vfork, and then the child prints certain messages by sleeping again and again. In case of the fork call, we have seen that the parent executes first, but over here you will see that the parent execution will be suspended until the child exits. Let me compile this program and execute it to prove what I am saying is correct. You see, the parent is not executing till the time the child has exited. Let me clear screen. Let me get another program, vfork2.c. Well, this program proves that after a vfork, the child runs in the address space of the parent. So no copy of the parent address space is created in the child. So the changes made by the child in the variables will be there in the parent process as well. Let me describe the code quickly. We have a global variable containing 54 and a local variable containing 100. After a vfork, the child executes first, increments these two variables and display the values. That is, the local variable will contain 101 and the global will contain 55. Once the parent executes, it will have the new values in these two variables, which will prove that both the parent and the child executes in the same address space. Let me compile this program, vfork2.c, and let me run it. So you see, inside the parent, you get the incremented values. Last, let me prove that the vfork is efficient than the fork. Let me get vfork 3.c. Okay, let me vim it first. vfork 3.c. You see there is a loop which is running 100 times, and we are creating processes using vfork. Let me save and exit this program. Let me compile this. And let me execute it. Let me time it so that we should know how much time it is taking. So it just takes 5 milliseconds. Let me make changes in the program, and instead of vfork, let me use fork this time. Let me save and exit, compile it again, and execute it. And you will see, since we have done fork now, so it will take more time, much more time as compared to the vfork. Maybe it will take about 15 seconds, if not less. Okay, so it is taking about 11.383 seconds, which is far more than what vfork is taking. Let's fall back onto the slides. Well, dear students, this inefficiency of fork system call was handled in the later versions of Unisys, in which fork system call was implemented using a technique called copy on write semantics. And what happens in this technique, instead of duplicating the entire process address space, the fork call just duplicate the parent page table and creates the required data structure like task struct for the child process. See this picture. Suppose this is a parent process, and this is a page table of the process, and this is the memory, and this page is pointing to this frame. If the parent calls fork, and the fork which is implemented using the copy on write semantics, not the entire address space of the child is created, but the child just gets his own page table, and that page table is exactly the replica of the parent page table. So if the parent page table is pointing to this frame, the child page table is also pointing to the same frame. So both parent and child use the same memory address space, and the reading is going okay. But the question is, what happens if the parent or the child process tries to write this page? So remember, whoever, whether the child or the parent, tries to write the page, a new page is copied and placed in the page table of that process. Suppose the child tries to write. When the child tries to write, a page fault occurs, and a copy of this page is created in the memory over here, and the address of this frame is placed in the page table of the child. So this way, only few pages of the parent are duplicated for the child process, and rest all of the pages are shared. So this is how the fork these days is implemented, that is, using copy on write semantics. This also shows the same idea over here. Parent and the child both are pointing to the same pages inside the memory, and whenever either the parent or the child tries to write these pages, a page fault occurs, and you see over here the page table inside the parent is pointing to this frame, while the page table entry inside the child is pointing to some other frame. Well, dear students, single Unix specification version 3 marks vfork as obsolete, so better not to use vfork. Let's talk about the concept of orphan processes. Well, dear students, if a parent has terminated before reaping its child or children, the child process is still running, then these child or children are called orphan processes. There is no concept of orphan processes in Unix. So these orphan processes are adopted by either init in old systems or systemd, system daemon in the newer ones, which do all the reaping. Let us see this concept on the terminal. Let me clear screen and let me add a program orphan.c. Okay, you see the fork is done over here and the child process is printing its ID and entering in a while loop. So the child is continuously running while the parent is printing this line and exiting. So that means the child process will become orphan. Let me compile this process orphan.c. Let me clear. Let me echo the ID of the shell and now let me execute this program. Excuse me. You can see the parent has terminated. The ID of the parent was 25007 and the ID of the child was 25008. You can see the parent of the child process is 992. If I do PS, you can see this 25008 is still running, and if I do PS-L, you can see the parent of this 25008 is 992. So that means this is not an orphan, rather this has been taken over by some other process. Let us check out which is this process having the ID of 992. Let me do ls-l from the proc directory to this directory and let me see this executable link, and you can see that this process 992 is actually the system daemon. So it is proved that all orphan processes are taken over by the init or the system daemon process, which is responsible for reaping the process, that is, clearing all the memory structures held by that process in the absence of its parent. Let me kill this process a.out having the ID of 25008. Let me confirm it. It's gone. That's great. Let us fall back and let me move ahead and now talk about another concept, that is zombie process. Well, dear students, processes which have terminated but their parents have not collected their exit status and has not yet reaped them are called the zombies or defunct processes. When a process terminates but still is holding system resources like the task struct, the various tables maintained by operating system, it is said to be half alive and half dead. Because it is holding resources like memory, but it is never scheduled on the CPU, because it never gets inside the ready queue. Remember, dear students, zombies cannot be killed by a signal, not even with the silver bullet, that is sig kill. The only way to remove them from the system is to kill their parent, at which time they become orphan and adopted by system D. Let us move on to the terminal again, clear screen, and let me show you a zombie program. Well, you can see after the fork, this is the child process, which is of course exiting by showing its ID, and this is the parent process, which is displaying its ID and entering in a while one loop. So the parent is busy in the while one loop while the child has terminated, so nobody has reaped the child, so the child has become a zombie. Let me clear screen, gcc zombie.c. Okay, you see this is the ID of the parent 25028, terminating child with PID 25029. If I press enter, you see the shell is not appearing up. This is because the parent process is still running in this case. Let me move on to another terminal over here. Let me do ps-a, and you can see, yes, this 25029, this is the defunct process, that is the zombie process. Let's try to kill this zombie process. Let me kill 25029. Let me send it the default signal, that is the sig term. Let's check out. It is still there. We have not been able to kill it. Let me kill it with a silver bullet, that is signal number 9. Let us check out. It is still there. So it is proved that we cannot kill a zombie process even with the silver bullet. So how to kill it? Let us kill its parent. Let me kill 25028. This process, that is the parent of this process. And let me check out again. You see, the process is no more there. Actually, what happened is when we have killed the parent, the zombie became orphan and is taken over by system demon, and it has reaped it. Let me move back to the slides again. So with this much discussion on the orphan and zombie processes, we have concluded that a parent process must monitor its child processes as the same is required in this real world as well. Well, dear students, in the Unix world, a parent process can monitor the execution or termination of its child processes using the wait family of system calls. And let us start with the first and the very basic call of wait. And this wait call, when called by a parent process, it gets blocked. It gets blocked until any of its child terminates. And we all know that the child process returns its termination status using the exit call, and that integer value is received by the parent inside this status argument. And this wait call actually returns the PID of the terminated child in case of success. Remember, this wait call is used to notify parent that a child process has finished running, or to tell the parent how a child process has terminated. Let us see an example that shows the use of this wait call. Let me clear screen. Let me man first. Man wait. So please do see the man page of the wait PID and the wait ID call. Let me straight away move on to the sample code of wait1.c. This is more or less the same code. Over here you can see the parent code is calling this wait system call. So the parent executes first after the fork, so it will be blocked over here. The child executes slowly, and finally it returns the exit 7 value to its parent. This 7 will be received in this status, and this wait will return the PID of the child, which are shown over here. Finally, the parent process will return 54 to its own parent, that is the shell program. Let me compile it. Wait1.c ./a.out. Well, you see, this is the ID of the child 25069, and once it exits, the parent says return value of wait is 25069, which is the ID of the process, and the status is 1792. Well, I think it should have been 7. So why it is 1792? Let me first check out whether the shell program has received the correct value. Yes, this 54 has been received in the shell environment variable $?. This is correct. But this 7 is not actually there in the status. The status contains 1792. What is the reason? Let us fall back to the slides and try understanding this. Well, dear students, a process can end in 4 ways. It can successfully return, or it can return in case of some failure. It can be killed by a signal. It can be stopped by a signal, or it can be continued by a signal. All this information is kept in the status argument. And the status argument, although an integer, its lower 16 bits are of our interest. Being a programmer, you can decipher this information using bit operators or using the available macros. Let me talk about the normal termination case. excuse me, when a process is terminated normally, the lower 7 or 8 bits will contain 0 and the upper 8 bits will contain the exit status. Can you think of writing a program using bit operators that will check out whether these lower 8 bits contain 0? And if yes, then find out what these upper 8 bits contain. And that will be actually the 7 which we are expecting in our previous code. Let us move on to the slides and see this part in wait2.c. Well, this is the same piece of code. As far as the child is concerned, you can see it is printing some messages and finally exiting with the value of 7. Well, over here you can see some bit operators in action. Well, we are getting the lower 8 bits. I am bitwise ending the status argument with 8 ones, that is 0xff. So this will give me the what is there in the lower 8 bits. And to get the value in the higher 8 bits, I'm right shifting the status with the value of 8. So I will get what is there in the over here exit status. So these upper 8 bits I will get in this, and over here I'm going to get this 0 in case if it is 0. And this if statement actually executes only if the process has terminated normally and if the lower 8 bit contains 0, and in that case it will print the exit status. So let me run this program, compile it and run it and see does it return 7 this time. Well, yes, we have got 7. Okay, let me fall back to the slides again. Okay, so once again, dear students, now let me decipher the other information as well. We have seen that we can find out if a process has terminated normally by checking out the lower 8 bits which will contain 0. And if the upper 8 bits contain 0, that means the process has killed by a signal, and that termination signal will be there in the lower 7 bits. And remember, this bit at index number 7 or at position 8, if contains 0, that means no code dump file is generated, and if it contains 1, that means the code dump file is generated. Well, if the lower 7 bit contains all 1s, that means the process execution has been stopped by a signal, and the stop signal is there in the upper 8 bits. And if the entire 16 bits contains 1, that means the process has got the sig continue signal. We can always write down code using bit operators to decipher all this information. Let me fall back to the terminal again and see if I have an example showing this in wait3.c. Yes, I have that. Okay, so over here what I'm doing is, yes, I'm calling a function display status, and I'm passing this function this status value of the wait argument, and this display status function will of course decipher this status argument and print appropriate values. Okay, so you can see the function over here. First of all, the normal termination, which we have already discussed. In case of normal termination, the lower 7 bits will contain 0 and the high 8 bits will contain the exit status. And the other 3 reasons are killed by a signal, stopped by a signal, and continued by a signal. In case if a process is killed by a signal, that means the higher 8 bits contains 0 and in that case the signal number will be there in the lower 7 bits. And in case if I want to find out whether a code dump file has been generated or not, well, this is the code which is doing that. I am getting just what is there in the bit at index number 7, and if it contains 1, I say code dump file is generated. Finally over here, if the process execution has been stopped by a signal, then this is the case. The lower 7 bits will contain all ones, and the high 8 bits contains the signal number. In case of the continuous signal, all the 16 bits of the status argument will contain 1. I hope this makes sense to you all. Let me show you one more thing in this code before I execute it. This piece of code, actually inside the child, what I'm doing is I'm doing a division by 0. That means the child will be given sig FPE by the operating system kernel. So if it will get the sig FPE, the status argument will contain that information, and that information will be displayed on screen. And over here we will get my child was killed by signal number, and I think the signal number of sig FPE is 8. And of course the code dump file will be generated. Let me compile wait3.c and let me execute it. Well, my child was killed by signal number 8. The code dump file is not generated. Let me check Q limit. Well, the code file size is 0 over here. Let me say Q limit -c unlimited. Let me check out again. Well, this is unlimited now. Let me clear screen and let me execute again. And now the code dump file is generated. You can see the code file is also generated. That is great. Let us move back to the slides again. Move ahead. Okay. Well, if bit operators are tricky for you, there are certain macros that are available in this header file. USR include x86 blah 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 bits and wait status.h. These are the 4 important macros. With exited, we pass this status argument to with exited, and if this macro returns true, that means child exited normally. And then we check wexit status we use this macro to get the exit status. With signaled, this macro returns true if child process is killed by a signal, and if it is killed by a signal, we use this macro wterm sig to get the signal number, and wcode dump to get the information whether the code dump file is generated or not. With stopped, this macro returns true if the child process is stopped by a signal, and if it is stopped by a signal, we can further use wstop sig, which will return the number of signal that has stopped the process. And finally, with continued, this macro returns true if the child process was resumed by sig continue. But whatever we have done using the bit operators can be done using these as well. Let me fall back over here and let me do less USR. Let's first see the header file bits wait status.h. Excuse me. Well, this contains the definition of these macros. You can see wexit status. These are the bit operators that are used, wterm sig, with signal. So this all we have done in a previous example. Let me use vim wait4.c, and this actually is the same program, exactly same program. You can see the child is doing a division by 0 and the parent is calling the display status function, but this time the display status function has not been written using the bitwise operators, rather it has been written using the macros. For normal termination, we are checking if exited is true, then we display that the child is terminated normally, and the exit value is in the macro wexit status. And similarly we have done for the killed and the stopped and the continue signal as well. Let me just run it so that you should have an idea that whatever we have done using the bit operators can also be done using the macros. So that is great. Let us fall back to the terminal again. And now let's talk about the limitations of the wait system call. Well, dear students, using wait, it is not possible for parent to retrieve the signal number using which the execution of a child process is stopped. Moreover, it is not possible to be notified when a stopped child has resumed its execution. So that means whatever we have studied over here, yes, the first two things, normal termination and killed by a signal, these two informations can be gathered using this wait call, but these two informations cannot be gathered using the wait call. So first limitation is this, and the second limitation of the wait call is that it is not possible to wait for a particular child. The parent can only wait for the first child that terminates. And third limitation is it is not possible to perform a non-blocking wait, so that if no child has yet terminated, parent get an indication of this fact. Well, let's see this other example that proves our concept of limitation of wait. Wait5.c. This is the same program as wait3, I think. The only difference is that we have a while one loop over here inside the child process, and rest everything is same. Let me compile this program, wait5.c. Let me execute it. So I am child and my PID is 25221. Let us move on to another terminal and check the status of these two processes, the child and the parent. ps-la. Okay, so you can note we have two processes, two a.outs, 25220 and 25221. The parent is sleeping and the child process is running, of course. Let us send the child process sig tstp kill-20. This is the signal number of sig tstp, and the PID of the child is 25221. Okay, and let me do ps-la, and you see the child process status is now T. It is traced. But over here you can see the parent is not notified. The parent is not notified that the child process has received the sig tstp signal. So this is the limitation of the wait system call. Let us fall back to slides again. Well, dear friends, you can write down other sample codes as well to find out the other limitations of the wait system call, but let me move ahead and talk about the wait PID system call. Well, with the passage of time, Unix designers have added a number of variants of wait system call, like the wait PID, wait ID, wait3, and wait4. Well, this is a wait PID call. Do read the man page and let me describe it over here. The first argument to wait PID is the ID of the process for which the parent process wants to wait. And if this is greater than 0, then the parent process waits for the child whose PID is given over here. And if we give a -1 over here, that means wait for any child. And if we give a 0 over here, that means wait for any child process whose process group ID is the same as the calling process. And if we give something minus, for example, less than -1, suppose I give -54 over here, that means wait for any child process whose process group ID equals the absolute value of this argument. Okay, so this is the first argument. As far as the second argument is concerned, this we all know about, that is the status. And this is the third option, third argument, which can be the bitwise ORing of these three values. And these three values can be seen in this header file, wait.h as well. Well, we can write down w untraced over here, which means also return information when a child is stopped by a signal, and this is what we wanted. W continued also return information about stopped children that have been resumed by delivery of sig continue. So these were the two limitations of the wait call. So if you write down w untraced bitwise or w continued over here, it will solve the issue. The third macro we can use over here is w no hang, that performs polling. That is, if no child specified by PID has yet changed state, then return immediately instead of blocking. Let us move on to the slides and see the example of this wait PID. When wait PID.c. Well, this is the same as wait5.c. We can see the while one over here, and well, the only difference is this wait PID call. This wait PID call. In the previous version, we have just the wait call over here. You can note the first argument, that is the PID of the child, and this CPID is the same as is returned by the fork call. So we want to wait for this child process. This is the status argument, and the third option is w untraced and w continued. W untraced means we want to cater for if a child process is stopped by a signal, and w continued means we also want to cater for if a child process is receiving a continuous signal. Rest of the code is the same function which we have seen before as well. Let me compile this program, waitpid.c. Let me execute it. Okay, so both are executing over here. So let's move back over here. Let me do ps-a. Okay, let me do al so that I can see the parent as well. Fine. So this is the parent process 25257, which is sleeping, and this is the child process which is running 25258. Let me send the signal sig tstp, that is, let me suspend the child process. Let me say kill -20, which is the signal number of sig tstp, to the child process having the PID of 25258. Remember, gentlemen, over here both these processes are running, and I am sending this signal to the child process over here. And now if I fall back over here, you see the parent is notified. The parent is notified that the child has been stopped by signal number 20. So wait PID is always a better option, as it is more powerful than the simple wait call. Let us fall back to the slides again and move ahead. Well, dear students, I think with this background knowledge, you will be able to learn the use of wait3 and wait4 calls, which also returns process resource usage information about the terminated child to the parent. The current calls of wait3 and wait4 to the wait PID calls are also shown in bold over here. And for further details, please read the manual pages of these calls. Okay, that is all for today's session. I hope it was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. See you next time. Wish you all the best. Happy learning, and Allah Hafiz.